Cool. So, 1 second. Hi, everybody. I'm Anthony. I'm a PhD student at Stanford University, working with Ram Rajagopal and Abbas El Gamal. And so today I want to, take a brief side switch from the previous talks and talk about some more methodological work on tool development that we've been doing for expansion planning methods. So as everyone here knows, the electricity grid is changing a lot. But just to get a sense of the scale of the transformation, although, like I said, I'm sure a lot of you know this, transmission capacity, for example, is projected to be increased by 2 to 5 times over the next 30 years. And so this is a huge investment. It means building one new transmission line for every one that exists today, which is totally unheard of. And so importantly, effective long-term planning tools, not just for policymakers guiding policy, but also for decision makers who are deciding where to build these lines, how much capacity to build, and so on, will be really key over the next 2 decades, 3 decades. And so the mathematical framework that we use to kind of study this is called expansion planning. So here I have a small network with some generators and some loads. And the idea is we need to connect the little green generator to the rest of the loads. And so in this particular example, we build 2 new transmission lines there to connect that generator to the loads. And that's kind of the optimal expansion plan. And traditionally, this classical approach to expansion planning, can be set up with two variables. So you have your operation decisions, X, and your network investment, theta. And then you put this together into some problem that you call your expansion planning problem with the investment costs, the operation costs, and lastly, a set that couples the investment variables and the operation variables through a set of constraints. Okay, so probably review for a lot of you. But so these traditional expansion planning tools are fabulous for a lot of different applications. But we have to remember that they were designed for vertically integrated utilities, trying to minimize costs on small and medium-sized networks. But today, there's a lot more stuff going on. So for one, today we have wholesale electricity markets throughout the US. So somehow you need to capture those market dynamics and still be able to model objectives specific to individual participants in the market. So you might care about, let's say, the emissions across the network. You might care about, let's say, the surplus available to the consumer, and so on. You also want today's methods to scale to much larger systems. You're no longer planning a small region in Oregon. You're planning the entire Western interconnect, which has thousands of nodes. And then in addition to this, you want these tools for decision makers to be interpretable. So importantly, in practice, a lot of the transmission and generation investments are being made somewhat heuristically by humans, sitting in a room deciding, okay, we'll build the line there, we'll build the line there. And so for these types of expansion planning tools to be useful, they need to understand what the results are and why they're saying, build this here, build that there. And then lastly, we think that for this goal of interpretability, you really want something that's interactive, that the planner can interface with and kind of change, let's say, inputs and assumptions and see how that changes model outcomes. Of course, you can kind of do this with uncertainty analysis, but the idea is there's always going to be something you didn't put in initially, and you want to understand how that changes the results. Okay, so that's kind of the goals for a method, and today we'll talk about how to do that. And as it turns out, we took a lot of inspiration from a similar method, or from a method used to solve optimization problems in machine learning. So in particular, basically every machine learning model today is trained using gradient descent. And this algorithm is super versatile. You can plug in basically any continuous optimization problem, and it works pretty well. It's very scalable, as evidenced by the huge models that are being trained today. Although machine learning itself is not very interpretable often, the gradient descent algorithm is. It's simply just a repeated sensitivity-based update. And finally, you can tweak the solution given new data, because gradient descent is really amenable to warm starting. So our high-level approach in this talk is just going to be, can we apply this algorithm two expansion planning problems. And can we use that to kind of unlock, more versatile objectives and more scalable performance? Okay, so for this first aim, let's go back to our traditional expansion planning model up here. And so this is basically just one big joint optimization problem over both investments and operations. But instead, we can decompose this into kind of a two-step decision-making process, where we first choose the investments in our outer optimization problem. And then given those investments, we choose optimal operation. So we're going to call this X star of theta. And the idea is that there's a function now, X star of theta, that maps our investments to optimal operation decisions. So this says if I build, this generator here and this transmission line here, what is the, day-to-day operations? What are the fuel prices, or sorry, the electricity prices and the generator schedule is going to look like? And so instead of thinking of this as part of the optimization problem, let's just think of X star as some really complicated function. It's kind of, in a black box. So in this framework, then now you kind of have a single optimization or an optimization problem just over theta that just happens to have this really complicated function inside. And, so why might you do this? Well, for one, in this framework, we can change the objective in the outer problem from C, which was our operation cost, to H, which could be basically anything. And so the idea here is that this could be, for example, the surplus available to the consumer or the total emissions. But, you might say, okay, well, you can do this with normal joint optimization. In this case, the operations are still dispatched using market cost. So in practice, electricity markets are cleared by cost, and I don't think that's going to change anytime soon. But you as the planner, let's say as a state government or as a utility, might care about different objectives than what the market cares about. So the utility, for example, will care about the surplus to their consumer, and the state might have emissions targets and things like that that they want to meet. And so this is the right way to model that framework. But it comes at a cost. And so when you solve a problem like this, it's called a bi-level optimization problem. These are sometimes referred to as Scalable games or mathematical programs with equilibrium constraints. And the long story short is that they're very difficult to solve. They make the problem non-convex and all kinds of things like that. So just to give some examples of what this might unlock. So here's our previous cost expansion or cost-based expansion from earlier. Now, if you change the objective to the consumer surplus at node 2, so basically the price the consumers at node 2 will have to pay, then you'll see that the transmission investment changes quite a bit. And so the idea is if the utility at node 2 is being told, build new transmission to connect this renewable generator source, then this is actually the investment they want to build because that'll help their ratepayers the most. And in a third scenario, if you're the state government trying to build transmission to connect renewables in order to abate emissions, you actually want to connect or build a line this way. And because that will kind of change, let's say, the market dynamics. And as it turns out, that'll displace different generation sources. Okay, so how does this solve traditionally? So just in general, this is a non-convex, or this bi-level optimization problem can be reformulated back into a joint optimization problem. But when you do so, it becomes a non-convex quadratic program, which is NP hard to solve in the worst case, and just in general, a pain to deal with. And the two standard approaches for doing so, first is to kind of apply a convex relaxation to said program, and then use some sort of branch and bound method to find an exact solution. So this will always find you, an optimal solution, but it's exponential complexity in the worst case, and in practice struggles with very large cases. And then second, you can maybe find an approximate solution by using an interior point method. However, these things also suffer from cubic complexity and empirically find very poor solutions as the size of the problem increases. Okay, so our approach is going to be to use gradient descent instead. So specifically, we're going to apply gradient descent directly to these investments theta. And what does this algorithm look like? Well, we just alternate between step 1, which is kind of evaluating the operations simulation and computing gradients, and step 2, which is updating the investments. And what's nice is that this has this nice interpretation as repeated sensitivity analysis. So you start off with some initial plan, maybe picked at random or something, and then you analyze the sensitivities, how things like emissions or prices or costs change with respect to capacities. And then you update your plan and obtain the new result, the new supply mix. Okay, so this is our proposed approach, but there's only one problem with this, which is that you might recall that this X star object that's being differentiated, this function, is actually the solution to an optimization problem. So how do you, differentiate something that basically, calls a whatever MOSEC or some solver and finds the optimal solution to an optimization problem? And that's a very difficult thing to do. But as it turns out, there is a way to do it, and it's using something called the implicit function theorem or implicit differentiation. So this is a tool that's being used heavily in physics-informed machine learning. And we think it has a lot of applications to more traditional problems in power and energy. And in particular, this lets us differentiate through the entire energy simulation or energy problem. Okay, so, and this is kind of the main technical drive of the work, but we're going to leave everything in this yellow box and just kind of move on from it. So how does this do? Well, so the first thing we did is we compared it to the said interior point method I mentioned from a few slides ago. And so you can see that the baseline method, both in terms of runtime and in the actual costs, scales very poorly as the number of scenarios in some energy problem that we solve increases. But in contrast, the gradient descent method scaled very well to larger cases. So it's not exact, it's not perfectly optimal, but it gets you close to an optimum most of the time, and it maintains that property as the system gets larger. And so just to see this in more detail, we looked at kind of how the problems or how the performance of the algorithm scales with both the number of nodes or the size roughly of the network and the number of scenarios. And importantly, as you increase the size of the network, you get roughly linear scaling for gradient descent. And second, you get efficient parallelization. So if you have a problem with, let's say, 1,000 scenarios, and you have a parallel machine with 1,000 cores or 1,000 threads, then you can kind of evaluate all those simulations in parallel and compute their respective gradients in parallel, and then aggregate that information to do an update. And so we have empirical results on this showing that it kind of aligns almost exactly with the theory in practice. And second, we have some theoretical work in a recent preprint that actually shows this, through theorems and proofs. And finally, what we're most excited about in this work is that we can use this, we think, in some sort of interactive planning tool. So like I said, you can warm start gradient descent. You can initialize it with any solution, such as the solution you found on your previous kind of run of the algorithm. And this could enable some sort of interactive planning study. So this is the exact same plot from a few slides ago. But the idea is, first, the planner takes in some data and some assumptions and solves a really high fidelity problem. And then second, they update their assumptions and then receive a new plan. And this maybe happens at a much faster pace than, the initial high fidelity. So just to see some examples of this, depending on how much you change the parameters, you can achieve upwards of 100 times speed up. So if it took you 2 hours initially to solve the problem, then it might only take you 1 minute to receive your updated solution. And so, yeah, this is that example. So we, as a case study, we solved a 500 node model of the Western US interconnect using data from the PIPSA USA dataset, which is a great data set for US grid stuff. And we used 1 year of hourly data. So the total system has, over 50 million variables in total, and it takes a few hours to solve initially, but only a few minutes to update when you want to change the plan. And so on this exact case, with the full 500 node model, we were able to do, let's say, a sensitivity analysis for storage. So we solved it, and we wanted to know, okay, if I change the cost of batteries, for example, how does investment change? And what's interesting here is that, okay, as expected, you see a dramatic change in storage investment. That's not too exciting, but you see almost no change in generation and transmission investment. And so this is the kind of thing that a planner could go in, fiddle with the knobs, and see the results from. And this is what we're hoping to do with this tool. So in conclusion, this work has all been about bringing gradient methods to the field of expansion planning. And we think it has these nice properties that lets us, model diverse problems and scale to big cases, and importantly, make things, interpretable and interactive for planners sitting, at the decision table and kind of making real decisions about where to build new transmission lines and generators. One challenge with the method I've described is handling integer decisions, but that's something that's future work and that we're handling right now. But in general, we're hopeful that this could unlock new possibilities for planners and help kind of accelerate decision making around this. So thank you.
Thank you, Anthony.
It's fine, I can just see. Thank you very much. So I had two questions. First, if you could go back to what X asterisk was, I mean, I didn't quite understand why you mentioned it was a black box beginning, and I was trying to link to the implicit function theorem.
Right.
Is it just like a function you feed whose argument is X, or what would be the solution to another optimization problem? That's the part where.
Yeah. So let me actually
Right.
see if I can find the slide later. So the idea is that X star it solves an optimization problem that chooses like the operational decisions. So in practice, the way you evaluate X star is actually by like modeling the problem in your favorite modeling language like Pyoma or CVXPy, calling a solver, and then extracting the results. But and the reason I'm calling it a black box function is because, if you have some access to the derivative through this theorem, you can just think of it as a mathematical function like anything else. So you can think of it just like, f of x equals x squared plus 2x or something like that. It's just really complicated what's happening. I don't know if that answers your question.
And then my second question was, so when you said regular decision it's can be word started to feed initial, it isn't sensitive to the initial condition. So does it give a different sort of answer to your optimization problem depending on what you feed into it? What sort of initial condition started?
Yeah, we haven't observed too much sensitivity to the initial conditions in terms of the final performance. But what does change is like the runtime, like how long it takes you to get there. You can imagine if you start with a really bad plan and you're making these small incremental updates, it'll take you forever to find a good plan. Whereas in contrast, if you start with something that's already like a, strong candidate, then, of course, it'll take very little time to find the optimal solution. Yeah.
Thank you for the meetings and great work. So my question is that you're on the longest function that goes within an operating scheme are continuing. And that's why that's a big have you compared this version with other Unix console like Finish that was running Android and so but for the same problem can also apply Android which is not environment that have solved a large scale problem.
Yeah, that's a good question. We haven't really compared to Bender's decomposition. I mean, I would say we did some theoretical analysis early on, that suggested that Bender's decomposition wouldn't scale as well. And then I think if I'm like recalling correctly, applying Bender's decomposition to these bi-level problems, specifically where the objective, let's see if I can change this back. So we had this like H instead of C, it is much less obvious. So it's much harder to apply it to this type of objective than it is to apply to something where you have like the same, C equals H setting.
This is sort of like off maybe this is one.
Like in that optimization one that we were talking about before, what factors to be considered and are there ways kind of set how to use them?
In the X star function or in the outer? Well,
Behaviors, one case, but let's say one initiatives, right? So the third one, we're giving less solutions. Do you still end up with like multi scenarios?
yeah, so in this little case study, we only use a single scenario, just like 1 hour or something like that. But in our larger case study, we have kind of a full like grid model. So like for example, we use weather data from 2019 and then for the full year. And then we use NREL projections for like load growth and technology costs and so on.
Yeah, okay, so maybe it's similar to cause maybe the hallucination may not switch off. How does it kind of find those?
Oh yeah, okay. So then as the planner, you can kind of set like an implicit value. So what we do is we set some, value of emissions kind of, which isn't quite a carbon tax because like the participants aren't being exposed to that. You care about it. But then you can change those relative weights. Exactly, yeah. So
And